In Chapter 1, we built the language of sets and functions, the vocabulary of outcomes. Now we start computing with it. This chapter is about counting because, in the simplest model, finding the probability reduces to counting. In this video, we meet the equally likely model, the counting principle, multi-stage experiments, and a quick way to count all the subsets of a set. Here is the simplest probabilistic scenario, finitely many outcomes, all equally likely. Take a fair die, 6 faces, each just as likely as any other. The probability of any single face is 1 over 6. An event is just a subset of the outcomes. Consider the event role a prime, the faces 2, 3, and 5. To find its probability, we count. 3 favorable outcomes out of 6 total, so the probability is 3 over 6, 1/2. That is the whole model, favorable outcomes divided by the total. The catch is that the counting is often the hard part, and that is what combinatorics is for. The first tool is the counting principle, and it is about the Cartesian product from Chapter 1. Take a set S with 3 elements and a set T with 2. Pair every element of S with every element of T, and you fill a grid. The number of pairs is just 3 times 2, 6. In general, if S has m elements and T has n elements, their Cartesian product has m times n elements. To count a product, multiply the sizes. Flip a coin and roll a die. 2 outcomes for the coin, 6 for the die. So 2 times 6, 12 joint outcomes in all. And because the outcomes are equally likely, the probability of any one is 1 over 12, which factors 1/2 times 1/6. Combining unrelated experiments multiplies their probabilities, an informal first taste of independence, which we will make precise later. The principle extends to any number of stages. With R sets of sizes n1, n2, up to nr, the number of ordered tuples is the product n1 times n2, all the way to nr. Each independent choice just multiplies the running total. Here is the classic case, an urn with n numbered balls. Draw one, record its number, and put it back. Repeat k times. Each of the k draws has the same n possibilities, so the number of ordered sequences is n multiplied by itself k times n to the power k. This is sampling with replacement, with order kept, the first of 4 schemes we assemble by the end of the chapter. Here is a neat application. How many subsets does a set have? Take the set 1, 2, 3. To build a subset, go through the elements one at a time and make a single yes or no choice. Is this element in or out? That is one binary choice per element, exactly the indicator function from the last video. 3 elements, 2 choices each, so by the counting principle, there are 2 times 2 times 2, 8 subsets, from the empty set up to the whole set. In general, a set with n elements has 2 to the n subsets, 1 indicator bit per element multiplied together. So the whole of this video rests on one idea. When outcomes are equally likely, probability is counting, and to count choices made in stages, you multiply. Next, we sharpen the toolkit with permutations and combinations, counting selections when order does and does not matter.